My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar, and I'm happy to share with you all that. It's our 73rd International Physics webinar, and good morning to all. So hope you are well and safe from Corona pandemic. All we know that we are staying in a Corona pandemic situation, so we cannot continue our normal academic program inside the campus. We have to start our online program. You know that our Department of Physics, Pabna University of Science and Technology, have already started its online program, including online classes and online international physics webinar. So we are trying to adjust with this new normal situation. Today is a very important day for our department. Today I'd like to welcome you all to a joint session between Pabna University of Science and Technology and the Institute of Mathematical Science, Chennai, India, in condensed matter physics. And we have with us here today Dr. Ganapathy Baskaran, sir, Emeritus Professor, the Institute of Mathematical Science, Chennai, India, and Distinguished Professor, Indian Institute of Technology, Madras, India, and Distinguished Visiting Research Chair, Prime Minister, Institute of Theoretical Physics, Waterloo, in Canada, connecting with us from India, and he has already connected with us. So I'd like to welcome our speaker. So good morning, sir, and welcome to our International Physics webinar. And thanks for accepting our invitation in this Corona pandemic situation. So for those who are new, I'd like to inform that we have divided our webinar into three parts. First of all, we would like to introduce our speaker with all of you, and then our speaker will deliver his speech, and at the end we have a discussion session. So you can ask questions by commenting, and you can join with us by using the meeting link. I think you have already come to know the title of the today's International Physics webinar, and title is the Quantum Jump and Leap. And our speaker is Dr. Ganapathy Baskaran, sir, Emeritus Professor, Institute of Mathematical Science, Chennai, India, Distinguished Professor, Indian Institute of Technology, Madras, India, and Distinguished Visiting Research Chair, Prime Minister, Institute of Theoretical Physics, Waterloo, Canada. So Ganapathy Baskaran, sir, is an Indian theoretical physicist known for his work on condensed matter physics and strongly correlated materials. Baskaran is an emeritus professor of physics at the Institute of Mathematical Sciences in Chennai, India, and distinguished research chair at the Private Institute of Theoretical Physics in Waterloo, Canada. He completed his undergraduate education in Theodore College and the American College in Madurai, India. He got his PhD in theoretical physics from the Indian Institute of Science, Bangalore in 1975, and he has done significant work on the development of resonating valence bonds, RVB theory, for high temperature superconductivity in strongly correlated electron systems. His reformulation of RVB as a local gauge theory has opened new direction in this field. Of his other wide-ranging contribution to condensed matter physics, the most notable have been on fractional quantum Hall effect and the optimization problem. So in 1987 to 1988, he, along with P.W. Anderson at Bristol University, developed the resonating valence band theory to describe the behavior of high-temperature superconductor. He also known for his discovery of emerging gauss field in strongly correlated system and for his prediction of P-wave superconductivity in strong and of high temperature superconductivity in graphene. Prediction which water later experimentally verified. In 1983, he was the first recipient of the ICTP Prize awarded by the International Center for Theoretical Physics (CST) for young scientists in developing countries for work in physics and mathematics. He was a visiting scholar at the Institute of Advanced Study in the summer of 1996. He was also awarded the Shanti Swarup Bhatnagar Prize by the Government of India in 1990. So you can see his research area, condensed matter theory and strongly correlated materials, and you can see his Google Scholar ID, and his citation number is more than 6,500. Thanks all for all of your questions. Now it's time to go to our speaker. Sir, welcome you again. And I'd like to say thanks on the behalf of the Department of Physics for accepting our invitation, sir. So it's your time. You can start your session, sir.
Okay. Thank you very much, Pretam Kumar Das. I feel really honored and to be talking to the students at Pabna University of Science and Technology. Thanks to the department and all the faculty members and those who are involved in organizing this talk. It's really a pleasure to be talking to young students who can jump and leap. So I'm going to play a game of quantum jump and leap. So, Pretam, am I audible?
Yeah, you can
I continue, right?
Yeah.
Wonderful. So I have to acknowledge various organizations. My institute at Chennai, Institute of Mathematical Sciences, and Indian Institute of Technology at Madras, and Perimeter Institute of Theoretical Physics at Waterloo, Canada, and Department of Atomic Energy for giving me a fellowship for 3 years, and then later Science and Engineering Research Board, India, for a long fellowship and distinguished fellowship. So let me start by introducing my institute briefly. It's called Institute of Mathematical Sciences. We do theoretical physics, pure mathematics, and computer sciences. There are about 60 faculty members, 100 PhD students, and so on. So for young people, there are very interesting visiting researcher programs, summer school program, and so on. So please have a look at our website. If you find a resonance with any faculty members, or if you like to visit, please write to us. It's a great small institute. It's not a big campus, but green and beautiful. You can see sometimes birds like this. It's a green campus. And it is in a very crowded city. Those of you now from Bangladesh, you are also used to crowds like this. Now, however, you can take an auto rickshaw from our institute. In about 2 to 3 miles, you will see the beautiful beach, country catamarans like this. And I took this picture not long back in the early morning when I went for a walk in the beach. It's a beautiful, fishermen are fishing. So you have a coexistence of big city and nature. Now, I'm also associated with Indian Institute of Technology called IIT Madras. It's a very fascinating campus. It's a large area. It's like a forest. You see deers and all kinds of trees, and you see monkeys. In fact, I tell friends that often monkeys enter my room. And when I start talking theoretical physics, they run away. That's a way to chase monkeys. And also, I spent about 4 or 5 months at Perimeter Institute of Theoretical Physics at Waterloo. It's a great institute. It's a research institute similar to my India, Chennai, but it has extensive visitors program. There is also something called the Perimeter Scholars International. I would encourage young undergraduate master students look at it. They have a variety of programs, 1-year program and short-term programs. And also, it's a very special institute because it represents, it's an example of respect by an individual for theoretical physics as something that helps transform society. And that gentleman is Mike Lazaridis, the former owner of Blackbody cell phone. So he was fond of theoretical physics. At some point, he gave $100 million, and that's how Perimeter Institute of Theoretical Physics was started. Now he has given about $400 million. It's amazing. There are people like this all over the world. Kavli, Yuri Milner, Simons. In India, Tata, Alagappa, and several people. I'm sure in Bangladesh there are very enlightened, rich people. And it's very important for young people to sensitize them, because helping science eventually helps society in an enormous way. We have seen it repeatedly. And also, I wish to bring to your attention, to young people, a great institute from which I benefited a lot in my whole career, called International Center for Theoretical Physics at Italy. It was started by Professor Abdul Salam, a Nobel laureate. He said that science is very important for developing countries. So there should be a center where bright young students and faculty come from developing countries and assemble and meet with great people and continue the science in their country. That's how ICTQ was started, and it's functioning very well, and In fact, I encourage young students to look at the website and look at the kind of activity. They have activities for young students, undergraduate students, and senior students. I'm showing this because that's where I met first several physicists from Bangladesh. In fact, my contact started 1976. I have met several physicists all over the over years, and some friends with whom I am in occasional contact are Professor Shamsar Ali. I saw him a couple of years ago at Trieste, in the Third World Academy of Meeting, Science Meeting. Saiful Kondekar, he was a diploma student and he did a project with me. Now he's a big professor at University of Central Florida. Tibra Ali, I met him at Perimeter. He has some big connection to ICTP also and Cambridge University. So right now he is at Brock University. He's an outstanding string theorist. So, he's right in Bangladesh. And Mujibur Rahman, an old friend from ICTP, he's in Sultan Qaboos University at Muscat. So I'm very happy to recall this association that happened because of ICTP. ICTP also did something wonderful. It was called the BC Spin Schools. Unfortunately, it ran for a few years and then stopped. Now it's for young people like you to take it over, because it's a remarkable collaboration and it brought students from Bangladesh, China, Sri Lanka, Pakistan, India, and Nepal. That's BC Spin. And speakers from all over the world. There is no reason why it should not continue. Okay, so this is, sorry, after a long introduction, this is what I plan to do. I'll discuss about laws of physics and then how friendly quantum mechanics is, and about new players and science engineering, rules of the game, and some subtle issues in quantum physics, and then some foundational issues, quantum technology, quantum computers, and quantum reality. It's like a kind of a guided tour. I will give you a glimpse of this fascinating field of quantum mechanics. I decided on this topic because in the part of the country I come from, South India, undergraduate students are scared of quantum mechanics. Partly because it's very counterintuitive. It's not, doesn't agree with our classical experiences, our day-to-day experiences. And secondly, there is mathematics associated. So, but however, I will try to tell you that the mathematics involved is very simple, matrix algebra mostly. And then the concepts are basically well-defined, the rules. If you understand them, you can do wonders. It's like if you learn to drive a car, you need not know how a car works, but you can do wonders. You can fly a plane, you can drive a car, and so on. Okay, so what's different about human species? We have, our ancestors discovered fire, and we have communication, we have language, literature, art, philosophy, and science. And, we fight, and, we have organized war, we have despair. Fortunately, there is hope. And we cooperate. So science attempts to unify, unfold the secrets of nature. And understanding some secrets of nature has transformed science society, the way we think, perceive our smallness, at the same time, unlimited potential we have, social institutions, United Nations, cooperations. Now, behind all these things are the great discoveries in physics and biology, laws of Newton, Maxwell's equations, Darwin hypothesis, understanding space-time relativity, and importantly, quantum nature. Now, if you look at the evolution of human mind, and we talk about literature, we talk about art, and so on, quantum mechanics is one of the greatest creative act of human mind, people say. It involves discovery, guesswork, intuition, and so on. And if you look at the entire universe, starting from the beginning of the universe, there is so-called Big Bang theory. There are important quantum effects at that time. Then we have nebulae, galaxy, star, planet, sun. And if you look at the sun, it's a nuclear fission is constantly taking place. It's a quantum phenomenon. And sun sends its light, and it's a quantum photon. If you come to Earth, we have atmosphere, stones, mineral, magnets, metal. If you go deeply into every one of them, there is quantum physics. So living systems, planets, animals, there is a lot of quantum system, ecosystem. Then we come down to Earth, solids, liquids, nanoscience, molecules, and atoms. Of course, there is quantum mechanics, obviously, in an obvious way. Then when you go down deeply, proton, neutron, neutrino, pion, quarks, Higgs bosons, and so on, there is quantum. So quantum mechanics is all pervading. So it's important to understand it, and it's easy to understand. And if you look at the history of quantum mechanics, it's a fascinating history. It started with Planck's observation, I will describe it, then Einstein, Niels Bohr, everybody made educated guess based on intuitions, de Broglie, greatest, and Bose, who was in Dhaka, Schrodinger, Heisenberg, Pauli, Dirac, Schwinger, Feynman. So it's a collective effort, unique in human history, a forerunner to the collective character of modern science. If you look at modern science, it's very collective. People all work together. They use others' work, and slowly science progresses, and fascinating developments take place. And in fact, if you look at this year's Nobel Prize, you can see the importance of collaboration. For example, this chemistry Nobel Prize, which was given for gene cutting. Two ladies met in Puerto Rico, and they started collaborating. In 10 years now, they are Nobel laureates based on collaboration. So it's very important to collaborate. Now, what you see is blackbody radiation, burning coal, and Planck looked at it carefully and said that if you look at the intensity of the radiation coming out of the black body as a function of the wavelength, there is something unusual. You have a long tail, which can be explained by classical mechanics, but there is a maxima and there is a big hole. So we said it cannot be explained by classical mechanics, statistical mechanics, electrodynamics, and so on. So what did he do? He fitted this curve to a very beautiful function called what is called Planck distribution function. And in the process, he had to introduce a constant called Planck's constant, which bears his name. And that was the beginning of quantum mechanics. And then Bose, S.N. Bose, derived it using identical quantum particle nature. And we have Bose distribution, bosons and bosons. No stopping. That was the beginning of quantum mechanics. Nature smiled through a very simple clue. Now, it's amazing that if you look at the distant sky, at the very far end of the universe, even now you can see the relics of the beginning of the universe, which started as a Big Bang. So you see a 3-degree Kelvin blackbody radiation, as discovered by scientists long back, 3-degree Kelvin. We are living in about 300 Kelvin, so on. 3-degree Kelvin, beautiful blackbody radiation. It's a kind of saying that quantum mechanics was there at the beginning of the universe. Then, great contributions from our subcontinent, Bose, Raman, Saha, Chandrasekhar. And it's very important to bring to your attention, young Chandrasekhar was a student at Chennai in Presidency College. He was fascinated by quantum mechanics, even as an undergraduate student. He studied it deeply, and then used some existing theories and applied the laws of electrons in metals. That is, when electrons and metals are organized into what is called Fermi state. So he applied to technology also grew. So if you go to the origin of digital cameras, they say it's due to astronomers because they were trying to build very sophisticated detectors. So in the process, they gave some chips to photo company people, and now we have digital cameras. Now, this is something I like telling about. Americans sent 2 spaceships called Voyager 1 and 2 long ago, 1977. Right now, they are beyond 10 billion miles from us. In India, we call crore, 1 followed by 7 zeros. I'm sure you also have that. Now, the total power radiated by this thing which is communicating with us even now is about 25 watts bulb. And it travels nearly 10 billion miles, and we are able to detect it using quantum detectors, quantum sensors. And it is powered by batteries which use radioactivity. So it has been serving us the last 40 years. Great, so many discoveries. And if you look carefully, behind all of them, there is quantum physics. So I just wanted to show you. Right now, these voyagers have crossed so-called heliosphere, and it's outside. It's our messenger going out of our solar system to the galaxy. So we learn about Newton's laws, and it makes a lot of sense. For example, if I tell my grandmother or my uncle about laws of Newton, for every action there will be equal and opposite reaction and so on, they say it makes a lot of common sense. Good. So, but they don't have the power of mathematics to use it to predict orbits or to predict things. That's classical mechanics. So where we have certainty and well-defined equations of motions for positions, momenta, and so on. And from there follows hydrodynamics, electromagnetism, theory of velocity. So it has predict power and calculus helps. Now when we come to quantum physics, this certainties change and we have uncertainty, which is at the foundation of quantum mechanics. So that's why it's counterintuitive, and that sometimes people don't like it. Now, so the laws of physics are different at atomic scale. So Newton's laws gives over to laws of quantum mechanics. We have so-called wave-particle duality. And we say that even an electron is a wave, photon is a wave, also a particle, so there is de Broglie wave. And then we have a fantastic phenomena called quantum tunneling. It's amazing that I am sitting inside a room in my house and lecturing. So in quantum mechanics, I can imagine a state which is realizable in principle, that I am sitting inside the room and also I am sitting outside the room simultaneously. It's possible to achieve this or create such states with electrons or proton or some small molecules. But to create such a state with a huge object like me is very difficult. But however, quantum mechanics allows that. So most quantum phenomena defies common sense. Like tunneling says that I have a hard wall in front of me, so I cannot push and go through the wall. But according to quantum mechanics, there is a small probability that I can go through the wall and go to the other side without destroying the wall. This is called quantum tunneling. It constantly happens with respect to electrons and protons in your chips. For example, if you take your cell phone and there are field effect transistors where constantly electron tunneling is going on. In our own body, in biology, electron tunneling is going on, proton tunneling is going on. Okay. So now, since I am told that your school, your university has both engineers and science students, I wanted to bring this. Quantum mechanics has brought a new synergy between scientists and engineers. I'm showing you three pictures. Peter Shor is at MIT. He's a computer science and electrical department. He started as an electrical engineer. There is a famous quantum algorithm called Shor algorithm for prime number factorization. So apparently I have met Peter many years ago. We organized a talk at the Institute for Advanced Studies at Princeton. He visited, spent a couple of days. And it's amazing. He started as an engineer, learned quantum physics. And now there's a famous Shor algorithm, which is pushing frontiers of quantum technology. Then Love Grover, who is at Bell and Cornell, I have also met him. He is also an electrical engineering, I believe, from one of the IITs in Madras, India. There's something called a Grover algorithm, a search algorithm. So an engineer learned quantum mechanics very effectively and became famous, two engineers. Now here is Umesh Vazirani. He's at UC Berkeley. He's a computer scientist. He has visited our institute a couple of times. Some years ago, I met him at Waterloo. So he has an excellent course in his webpage. He has been offering this course on quantum information, especially meant for people outside physics. So you can go a long way in appreciating quantum physics and learning subtleties and becoming an expert in quantum mechanics if you know matrix mechanics or matrix algebra. So you can look at his website. And there are many, many fascinating websites and courses on quantum physics, which is understandable to electrical engineers, biologists, physicists, and so on. So you will see that quantum physics is a very friendly subject. At the beginning, it may look very strange and unusual, but the rules of the games are very sharp, and the mathematics involved mostly manipulation with matrices. And of course, if you do quantum field theory and so other things are different, but the underlying structure is very friendly and very beautiful. So, like in classical mechanics, we have Newton's laws. So you have something called Schrodinger equation, which is an equation for so-called complex probability amplitude of state of the system. So it will sound like a very strange language, but that's the way it is. So these states live in so-called Hilbert space. And unlike classical mechanics, you can imagine superposition of two states, states I and J, and they are also physically meaningful. So this is mathematics. And once you know these rules of this game and you know so-called Hamiltonian and play with it, you can do wonderful things, calculate and make comparison with experiments and so on. But mathematically, these are all very neat. But it leads to you something called non-classical correlation in quantum entanglement, variety of quantum resources. That's why it's very exciting also. So in classical mechanics, we have so-called phase space. Suppose you have n particles living in 3 dimensions. There is 3 n-dimensional configuration space and 3 n-dimensional momentum space. So put together, it's called phase space. Now, whereas when you go to quantum mechanics, the space is much, much bigger, even incomprehensible. And this is quantum mechanics gives stability to an atom. And you won't believe, that quantum mechanics is responsible for chemical bonding, formation of molecules, minerals, metals, alloys. And if you look at you are sitting on a chair, the chair is not giving up and you are not able to poke your finger through the table in a fundamental way because of Pauli principle. Because at the level of atoms and molecules, a molecule cannot go through another molecule because when it tries to press them, Pauli exclusion principle will come into play. So quantum mechanics gives stability, binding, and so on. Another fascinating thing about quantum mechanics is the notion of 2 types of particles called bosons and fermions, in honor of famous Bose. So, in fact, it's one of the fantastic discoveries that came from mathematics, that if you use the laws of quantum mechanics, you use the rules of the game, you are forced to define 2 kinds of particles called bosons and fermions, which have something different permutation symmetry. If we take state of containing 2 particles, 1 and 2, and if we permute their coordinates, for bosons the sign doesn't change, for fermions the sign changes. And what is experimentally measured is often the modulus square, so it doesn't matter. But however, they distinguish the particle. So now you put these particles together, you get complete different physics. You put bosons together, you can get helium-4 superfluidity, or you get lasers. If you put fermions together, you get metal like copper, very different behavior, coming from fundamental difference in their so-called statistics. Now, quantum matter is in plenty. The world is full of quantum matter. If those of you in solid state physics, you'll come across band insulators, topological insulators, holes, electrons, excitons, plasmons, and charge density wave, spin density wave. Variety of quantum phases exist. Now, one of the thing about quantum mechanics, it gives new hope to humanity. The miracle of radio communication, the miracle of science, the miracle of information technology, and the new possibilities. If you think about radio communication, Marconi discovered it. Maxwell discovered it when he tried to unify Ampere's law, Biot-Savart's law, Faraday's law, Gauss's law, and put them together into a mathematical framework. And he found it was a wave equation describing waves that move with constant velocity independent of their wavelength. And then he also computed the velocity of those waves. To his great surprise, with whatever numbers he had at that time, it was close to velocity of light, which was by then known. So that was a great discovery there of electromagnetic waves from a theoretical curiosity. Because Faraday didn't do it, Ampere didn't do it. It was Maxwell who put them together into a theoretical framework and discovered Maxwell's equations and electromagnetic waves, predicted their existence. 20 years down the line, Hertz produced it. And 20 years down the line, J.C. Bose, Marconi, and others communicated. No, the world is different. I am communicating with you through radio. It's a result of theoretical physics. Similarly, small chips, transistors, they all use quantum principles. They are responsible for communication and detection. So there are new possibilities. You're discovering solar energy can put the world in the right path to eliminate climate change catastrophe. A new discovery in genetic engineering can make us baby angels, quantum computers, room temperature, superconductivity, and so on. What you see is the solar power. Now, I wanted to just tell you about quantum physics that nature uses in the leaves and in bacteria. We all see, when you look at outside, there will be beautiful green plants and flowers and so on. If you go down deep at the molecular level, in so-called photosynthetic apparatus, this is a photosynthetic system of bacteria. Even bacteria use photosynthesis. What you find are protein molecules organized in beautiful patterns, and they embed so-called chromophore, another molecule. These chromophore molecules absorb the light, photon, one by one, and then this photon creates an excited state called an exciton. And this exciton runs around this circular disk coherently in a quantum mechanical sense, in spite of the fact it's in a wet, warm room environment, room temperature environment. This is a mystery even now. So-called quantum biology. How come nature uses quantum coherence in photosynthesis? Because that quantum coherence is very important, because the photon runs around, at some point it jumps, it's absorbed by so-called reaction center, which begins a cascade of reactions. So light is absorbed very efficiently and then converted into electron-hole pairs, and then they are involved in proton transfer and so on, which is what we do in batteries. So nature is doing it the most efficient way. This bacteria I'm talking about, there's some kind of purple bacteria. They live in deep muddy water. Even a single photon they don't leave. They efficiently use it and to produce. So we have to learn from nature about quantum mechanics, also about photosynthesis. So I want to tell you about modern electronics. When I was young, we used radios like this and we had walls. Now you have cell phones and so on. And behind this history are these great men. And the first three, Bill Shockley, John Bodin, and Pretam, are responsible for discovery of what we all enjoy, transistors, you all know. Then many people followed. Basso, Prokhorov, Kromer, and Kilby got, all of them got Nobel Prize. I just want to point out that in this first discovery, John Bodin, a theorist, used quantum mechanical understanding of solids in fundamental way. He used the idea that insulators have a band gap, and if you put in impurity, it creates so-called quantum mechanical impurity states and so on. That is when quantum mechanics was being developed, and the body used it. So without that quantum insight, we won't be here now in our modern science and technology. So it was quantum mechanics which worked effectively. I should also tell, very happy to tell that I had two opportunities to meet great John Bodin. Once, when I just submitted my thesis, John Bodin was visiting Indian Institute of Science, Bangalore, and I had an opportunity to talk to him for 1 hour. It was wonderful, actually. Then later, in 1987, I visited Urbana-Champaign, University of California, to give a colloquium, and John Bodin listened to my talk. And when I came out of the colloquium, many people shook my hands. I thought I gave a good colloquium. They said, no, it was an okay colloquium. But you made John Bodin to ask one question. Apparently, he never asks questions. So he asked me some questions. So I was very happy I had later discussed with him. I had also met his two sons, both are physicists. Anyway, this is just a side remark. But you can see the role quantum mechanics played in 1948 when they discovered solid-state transistor. Because they used basic ideas that you learn in your elementary quantum mechanics, with band gap, impurity levels, Fermi levels, and so on. There is another fascinating person and fascinating article there. Richard Feynman, a famous physicist, I'm sure you all have heard about it, theoretical physicist. He's a very special physicist. He wrote an article, and in fact, based on a talk he gave to a bunch of physicists. So he said, who are also involved, technology people and various kinds of different types of people. So he wrote an article called "There is Plenty of Room at the Bottom." His point is, why don't we use the way we use, rocks and stones and machines? Why don't we use atoms, molecules for information storage, create nanomechanics, use strange principles of quantum mechanics to our advantage? So he provoked the audience, and and he also constituted a prize, saying that if you achieve some of these things, I will give you this money. So it's a very famous article. I encourage you to people to look at this article. It's called "There is Plenty of Room at the Bottom." If you Google, you will get it immediately. Now, after some years, what you see is a ordinary microscope. You have your eye, and you have objective lens, and you have eyepiece, and so on. Now, it was Ernst Ruska who used, instead of electromagnetic wave, electron waves, because I told you that electrons are also waves. So he used them and built a microscope called electron microscope. He got Nobel Prize. And it could resolve at the scale of atoms and molecules, just quantum physics. Then these friends, Bennig and Rohrer, got Nobel Prize in 1986 for their discovery of scanning tunneling microscope. I have visited their lab, very humble apparatus. In fact, in this apparatus, in order to have a shock absorber, what did they do? They took a tire, cycle tire, and inflated it and put their instrument on that. And they put 3 cycle tires. So there was a cumulative effect, and it worked out as a fantastic shock absorber. So doing great experiments, you don't need very sophisticated. Of course, it's necessary, but at the beginning, you can do a lot with simple things. J.C. Bose is a outstanding example. He also discovered, what we call as transistor crystal detectors at the beginning, and then he had done wonderful things. So this is the principle. You have a tip of a metal, and then you have a surface, and then what you do is you apply a voltage, and then electrons tunnel from the tip to the metal surface. That's why it's called scanning tunneling microscope. Now, if you move the tip, depending on the distance from the surface, it move up and down, so it modulate the current. And using that, you can map atoms sitting on some copper surface like this. Or you can detect a molecule containing 8 cesium and 8 iodine atoms. So, miracle of quantum mechanics. Apparently, when Richard Feynman saw some of these pictures, he told that this was like a religious experience for him, because we have been talking about atoms and electrons and so on. None of us have seen it. But here is an experiment which gives you a shape of an atom or molecule. Then, miracles like modern new materials. If you take carbon, we are made of, our body is full of carbon. Carbon can make diamond, carbon can make graphite, carbon can make fullerene, nanotubes, wonderful things. So at an elementary level, quantum mechanics is at work, because these carbon atoms undergo sp2 bonding and form this beautiful honeycomb lattice. And then every carbon atom has one lone electron. They combine to give wonderful properties. And Novoselov and Game isolated this graphene by very elementary methods, very humble method, like putting a scotch tape on a piece of graphite and then peeling it off. And then they could do some interference experiment to show that it's a single layer, double layer. Now it has a big field, Nobel Prizes, and lots of activity in two-dimensional physics. I will not go into the detail. Now, let me talk for the next 5 minutes about superconductivity. You all know that if you pass a current through a copper wire or a tungsten wire, it will glow because of resistance, because it converts electrical energy, kinetic energy into heat. So it's very useful. But it turns out it's very useful if you don't have any dissipation also. That was discovered by Cameron back in 1911. He took mercury and cooled it down. At around 2 or 3 Kelvin, the resistivity dropped to 0, literally 0. So it's a new state of matter. No dissipation for electrical current flow. Then very soon, Meissner discovered that if you have a superconductor like this at the bottom, take a piece of magnet, the magnet will float. Why? Because the magnetic will give out magnetic field, and that field normally will penetrate in a material. But the superconductor doesn't like magnetic field, so it will push it out. So that acts like a force which acts against gravity, and it will float. So this is called the levitation. And this Meissner effect is an effect called perfect diamagnetism, a fascinating consequence of quantum physics, which works in superconductors. It has profound applications, including the one I have shown. So if you can levitate a bar magnet, then the friction between the two is only air. So if you can levitate a train, then the friction between the track and the train is only the air. So it can slide. It has been demonstrated that such magnetically elevated trains can go 2,000 kilometers per hour, supersonic speed. So I can come to Bangladesh in 1 2 hours or 3 hours in this train. Now, of course, in the normal supersonic, this magnetic levitated trains, you don't go that speed, maybe 400 kilometers, because at this speed of 2,000 kilometers, the body will burn. So you need special protection. But the point is, this made my friend Kitazawa, late Kitazawa, he's no more. He did fantastic work on high temperature superconductors. He became a science minister of Japan, and he envisaged several fascinating possibilities in a realistic way. He did calculations with engineers and developed. He said that we have a lot of solar energy, we have a lot of wind energy, so we can collect them in deserts and in oceans, and then create electrical power grid using superconducting cables. And then he made estimates. They had a big team. Said that if we do it, it will be cheaper than the money that we spend for our energy now. But it requires international cooperation and collaboration. Even though you use liquid nitrogen all along under the ocean, but still it is cheaper than. So, but unfortunately, it has not happened so far, but it's a futuristic thing. This is a consequence of quantum physics. A superconductor is a remarkable consequence of quantum physics. Unfortunately, we didn't have time to even tell about it, but that's the way it is. So there are, Kitazawa. In fact, in a talk I gave, in which Kitazawa gave a talk, I was summarized the conference talk. I gave a conference summary talk. I called it as Kitazawa's dream. So it's 10 years ago. So his dream is he will connect the entire world. You can see the tracks going through Bangladesh and Madurai, my city, where I'm sitting right now, going all over the world. No aircraft is necessary. You can go from place to place very, very fast. So again, international cooperation is necessary. Some of you young people, when you become future leaders, please think about it and implement it. So now I'm going to spend the next 10 minutes about this fascinating field of one of the applications of quantum mechanics called quantum computation. As I already told you, laws of physics are different at atomic scales, and you have quantum mechanics, particles behave like a wave. And then you may ask, can you define the wavelength of a particle? Yes. So the wavelength lambda is given by Planck's constant divided by mv. I'm sorry for a box because there's some incompatibility. So Planck's constant divided by mass times velocity is a de Broglie wavelength. You can estimate the de Broglie wavelength for a piece of chalk or for an electron moving with some velocity, and you will find the de Broglie wavelength of an electron in a metal is comparable to lattice parameter, which is like a couple of angstrom units. So these wavelengths are very, very short. They are not like meters and so on. Whereas you can have this de Broglie long wavelength with respect to light. So you can do wonderful things with it. So as I already told you, you can have linear superposition, you can have quantum entanglement and so on. I will explain to you what is a quantum entanglement. It's a very counterintuitive thing, which even made Einstein think deeply and make a statement at some point, it's not possible. What did Einstein say? Einstein, Podolsky, and Rosen. They said that if quantum mechanics is really true, the following weird thing will happen. So in quantum mechanics, if I have system A and B, their state is, and if they are not communicating with each other, their state is described by product of two wave functions, called it two kets. Now, if the systems communicate and if they interact, in general, it will be a sum of such products. Now, if you think about it, let me give you a simple example. Suppose I take a hydrogen molecule. There are two electrons. Let's forget about the proton. Let's say they carry this positive charge. Now, the two electrons, you all know, learn in your school, high school and college, that the two electrons will form a so-called singlet, which is a combination like this. An electron up, one is up, electron 2 is down, and electron 1 is down, electron 2 is up. So it's a linear superposition with the negative sign. This is what quantum mechanics tells you. But Einstein and these people argued that, okay, so if this is true, then let me slowly separate the two hydrogen atoms and take them apart. And then the spin function will remain the same because I'm not disturbing the system, I'm doing it adiabatically, very, very slowly. So let me say I have one electron in Dhaka or in Pabna and one electron in Madurai. If I have done it slowly, if I make a measurement and at Madurai and say that electron at Madurai is up, for sure you will find the electron at Pabna down, and vice versa. If I am saying it's down, it's in Pabna it will be up. So even though the two electrons do not talk to each other because they are far apart, there is no way by which they can communicate. But there is a quantum correlation, so-called non-local correlation. So Einstein said this is not possible. He called it a spooky action. And he said, because of this quantum mechanics, perhaps it's not true. But nature is much wiser than us. So apparently it is true. Now they have done experiments, not with respect to the hydrogen atom. So what you do is you have a source in which two photons are produced, two individual photons. And the photons have so-called polarization state, you all know. Circular line is polarized, left or right circular line is polarized state. You can call it as up or down. So these two photons are quantum mechanically entangled. And of course, photons move with velocity of light. So they have taken the photons apart and done the measurement of polarization. And they found even when they are separated by 200 miles, the strange quantum correlation or spooky action is true. And recently, our Chinese friends have done it with satellite and ground-based entangled object. So this is one of the most counterintuitive thing in quantum mechanics, but it is true, experimentally proved. So can we make use of it to our advantage? And in fact, I forgot the reference. There is a paper, a very elementary paper you may like to look at. Please do Google, called quantum teleportation. See, we all, you see in science fiction movies, a hero or heroine standing in one place, a machine comes and she disappears and she appears in a distant galaxy. We call it a teleportation. It's a science fiction. But now you can teleport, not a man or an elephant, but a quantum state involving some small finite dimensional Hilbert space. And that is achieved now. And that proposal is a beautiful theoretical game. Understandable, if you know elementary calculus and matrix algebra, you can understand that paper. Please Google quantum teleportation. So, okay, now let me quickly go through what is the difference between a classical computer and quantum computer. In a classical computer, you have switches which can be on or off. So using them, you build gates, AND gate, NAND gate, NOR gate. In quantum mechanics, you can superpose these two states as a complex state like this, with this condition. And in classical mechanics, you can have either on or off. But here you can have infinite possibilities. They are all linearly dependent. And if you look at, put them mathematically, every point on the surface of so-called Poincare sphere corresponds to a linearly independent state. So when you go from classical mechanics to quantum mechanics, all of a sudden you have gone from two states to infinite number of states. So this is counterintuitive, but that's the way it is. Now, you saw Poincare sphere. Recently, I was listening to a talk by a friend of mine, Joseph Samuel, who was at Bangalore. So if you take two such qubits, this is for those who are mathematically minded, please have a look at this paper. If you take two qubits, or the qubit that is there in a hydrogen molecule and go to triplet and singlet state, and look at the states that are allowed by quantum mechanics. there is a very deep mathematical connection to Lorentzian geometry that appears in relativity and general relativity. Mathematical connection, not physical connection. See, this is another thing that you will learn in physics, quantum mechanics. Mathematics is a great unifier. Mathematics that is used in string theory gets used in some places in graphic, or mathematics used in Dirac theory is used in topological insulators, and so on. So mathematics is a great unifier. So you see mathematics, Lorentz symmetry coming in an unexpected place. So these are all things to be seen. So in a classical computer, there are n bits, then the to the power of n states. For example, a switch 1 can be on, off, on, and so on. But in quantum mechanics, because of the so-called parallelism, I can, using this 2 to the power of n basis state, build any number of states, infinite number of states. Because even with 1 qubit, I can build infinite number of states. Now it's more infinity. So this gives you new possibilities. I will just schematically describe what is possible. Now, if you look at this picture, this is a schematic picture of a classical computer. In a classical computer, what do? You want to solve a problem. So you define the problem and create it as an initial state. Then you have an algorithm. And then it's a unique number of steps, sequence of steps. So this algorithm takes you along a sequence of steps and gives you the final solution. It could be multiplication, or it could be prime number factorization. It could be a long algorithm. It may take time. Okay. So there is a deterministic path to go from initial state to final state. This is what your and my computer or cell phone does. Now a miracle happens when you come to quantum computers. Now I told you, quantum mechanics has this possibility of infinite superposition. So there is a new resource. So quantum computer uses this new resource in the Hilbert's book. So quantum computation is a sequence of unitary transformations as defined by an algorithm and certain initial quantum mechanical states. Please don't worry if you don't understand. But the whole point is the following. In our classical computer, you had a single path, the red path, to reach the final solution. In quantum mechanics, because of the rules of the game, because of the laws of quantum mechanics, you have simultaneously infinite number of paths that is being sampled by the quantum system. This may look very counterintuitive, but that's the way quantum mechanics is. Those of you who have an urge, please look at Feynman's path integrals. In fact, Richard Feynman, whom I mentioned before, he reformulated quantum mechanics using path integral, which made a very close connection to classical mechanics. He said that in classical mechanics, particles travel in a different trajectories. In quantum mechanics, they take all paths, but then they take all paths with various probability amplitudes. And finally, what you see is the sum of those amplitudes. So this is called path integrals. Very beautiful mathematics. Very simple. At the beginning, it may look scary, but after some time, you'll start appreciating it, and you can illustrate many of these ideas using just simple matrix multiplications and so on. So that's how quantum computer becomes extremely powerful. So even if you have, they say, a computer having 100 qubits, you can solve the biggest challenging problem in the world now, or problem which are not easily okay. Now, if you this name quantum, if you do Google, appears in many places now in the modern context. Firstly, they're so-called qubits, because I told you that the electrons carry something called spin, which can be up or down. So nuclei also carry spins. Now, in terms of these are quantum degree of it, because their origin is very quantum mechanical and also relativistic. So it's not just a particle is spinning and then there is an angular momentum. It's something more than that. It's called a quantum relativistic consequence. So similarly, you can use Josephson effect and then bosons like light and so on. So these are all like gates that are used in things used in classical computers, up or down. So the states of nuclear spin or ion trap can be used to build quantum computers. Now, what can you do with this? You can do simulation, you can do quantum algorithm, quantum annealing, quantum optimization. People talk about quantum supremacy. Google came up with something, they say they built a quantum computer which can solve some problem which others cannot solve. Now, next week somebody else announced something. Then behind all this big game, there is something called quantum decoders. This is something very important. I will spend a minute explaining it. It turns out quantum mechanics is extremely shy, because we see the world as a classical world. Because quantum mechanics is shy and doesn't reveal itself. At some point, classical mechanics is sufficient, or Newton's laws are sufficient. Only when you go deep into the level of atoms and electrons, quantum mechanics shows up. However, I told you about superconductivity. There, quantum mechanics is not shy. It's a macroscopic phenomena. Quantum mechanics shows it. And also, you won't believe, if you take a piece of ferromagnet, like iron, magnetized iron, it's a quantum phenomena. Quantum mechanics at macroscopic scale. We don't appreciate it. Now people have started using it in creating quantum computers. So even though quantum mechanics is shy, but it's not that shy. There are places where it shows up in a dramatic way. As I told you, the very stability of atom is quantum mechanical. Hardness of a stone is quantum mechanical. But the question is, can we use it? Can we go use the quantum principle in a fundamental way? So here something remarkable comes. A quantum system like an electron spin or a nuclear spin or a state of a superconductor because of Josephine qubit never likes to be alone. It communicates weakly with the environment, the world. So that destroys the quantumness of the object that I'm talking about. Because the quantumness is something unique to, you can say, limited Hilbert space, or limited to so-called quantum states living in some corner of the Hilbert space. Now, if it communicates with the rest of the world, it goes into a much bigger Hilbert space, and then it becomes so-called decoherence. So the quantumness is lost. This is a big challenge now to experimentalists. When they try to build quantum computers, they face this question of decoherence. That is, the system remains quantum mechanical for milliseconds or nanoseconds or microseconds. They want to keep coherent for 1 hour or 10 minutes and so on. So these are big challenge. So it's a great topic called quantum decoherence. There are very simple models, for example, Caldera-Leggett model, where your qubit or two-level system is coupled to a collection of simple harmonic oscillators, and you can understand a lot of things. The many principles can be understood. And also, I wanted to tell you that those of you who are quantum-minded, who are excited by my talk or by quantum mechanics, you can do some of these experiments yourselves. Apparently, IBM has a quantum computer, several qubits, which is accessible to the public. So you can register and you can do experiments sitting at home through your computer. You tell them, and the experiment will run, and you will see the result using quantum computers. Similarly, I was told that I forget, somebody was telling that there are new other people giving quantum computers to the access of people and so on. So as I told you, the rules of the games are very simple. Basically manipulation of, if you are dealing with qubits, I can confidently say it's manipulation of, if you have n qubits, it's manipulation of 2 to the power of n at best matrix dimension of matrices, or direct products of several 2 by 2 matrices and so on. So if you understand matrix mechanics and linear algebra very well, you can become a great expert in quantum mechanics. Okay. Now let me end with one of the triumphs of quantum mechanics, because I have been talking about quantum mechanics. So you may ask, has it helped us in the recent time? Can you point to some great breakthrough in recent time? Yes, I can. You all have heard about the exciting discovery that took place 4 or 5 years called LIGO. This is a gravitational detector somewhere in the United States, North America. There are 2 such. So what you see is like a Michelson-Morley 2-arm interferometer, except that the arms are very long, like a few kilometers. What you have are mirrors, and here some laser source and another mirror and a light detector. So it's an experiment that you do in your undergraduate lab, maybe high school lab. Now you do this experiment, but you don't want to detect. You are interested in detecting gravitational wave. You remember great Einstein, who discovered, who founded, the founding fathers of quantum mechanics, lasers, special theory of relativity, general relativity, and also a great humorist, as a pacifist, and so on. He said that space-time is like an elastic medium, to put it very crudely. So it can undergo deformation and it can support waves the way elastic solid supports sound wave. So they are called gravitational waves. So it was a prediction which he himself didn't believe after some time. He said, no, it will be too difficult to detect. Okay, that was more than 100 years ago. Now some bold minds started thinking about it. Various people at Caltech and other places. They said maybe we should be able to. Weber, firstly, at Maryland, we should be able to detect it. So decades of effort has finally culminated in detection of these gravitational waves. So how does this instrument detect? So these gravitational waves that they detected, again, is fascinating to think about. 2 billion years ago, two black holes collided somewhere in the distant part of the universe. 2 billion years ago. So what will colliding black holes do? They will emit gravitational wave radiation. So this radiation travels for 2 billion years and it's likely to pass by Earth. Now this telescope, as it passes by, will shrink because the space-time is changing, is getting distorted. The telescope also distorted. So you will see it as some shift in the interference phenomena. Okay, it's easily said. How much is a shift? I will show you. So these two LIGO detectors at Hanford, some part of now Americans, in Livingston, two well separated parts. So they measure the interference pattern. And how do they measure? They measure basically strain. You all know strain. Change in length by the length of a body. Suppose I give you a piece of pencil. Its length is 10 centimeters. If I compress it, it may compress 1 millimeter, or a piece of steel rod. So delta L by L is called strain. Now you notice it is 10 to the power of minus 21. Now L is 2 kilometers. Even then, the delta L that will give you the ability to measure 10 raised to 21 is 1,000th of the size of a proton. I mean, we are familiar with 1 millimeter, maybe 0.1 millimeter. After that, you'll have to use microscopes and so on. Then you'll have to use STM to go to 1 angstrom. Then you cannot see the nucleus. But this instrument has managed to detect a change in length of a 1 kilometer arm by a length which is 1,000th of a proton size, 1,000th of a femtometer. Mind-boggling. How was it possible? Thanks to quantum mechanics. So again, please do a Google search. Rana Adhikari is the professor at Caltech. I had the pleasure of listening to him 5 years ago at Perimeter Institute before the LIGO discovery. He was describing their instruments because he's an expert on this quantum sensitive measurement instrument. It's like STM, but with much more orders of magnitude precision. So what do? They take a big mirror, which is 10 kilograms, and they have to isolate the center of mass from the rest of the world, where they manage to do it. And then they have 4 levels of feedback, quantum feedback. And I don't understand honestly, because I heard his talk and I read the papers also, but it's for young people like you to appreciate and understand it. Imagine you can measure a strain of 10 raised to minus 21. Without quantum mechanics, nobody would have thought about it. So even great Einstein, somebody was telling me, will not understand what's going on, because he discovered this. So that's the sensitivity that quantum mechanics offers. So this is quantum technology. So quantum technology not only useful in information, but it's useful elsewhere. So let me, I think I have just come to about 55 minutes. Pretam, how am I doing with respect to time?
You can carry another 10 minutes. Okay.
Okay, wonderful. I will wind up slowly. So we got some feeling for various quantum phenomena. Now I will last 10 minutes. I will elaborate my favorite subject, even though I'm not working on it, but I'm fascinated by it whenever I think about it. It's called quantum biology. Please don't bother if you don't know quantum mechanics. Because quantum mechanics, as I told you, it's a very simple rule. You can understand it using matrix multiplication. And the rules of the games are very well defined. Like, if you know driving the rules, you can drive very well. So later you can understand machines and so on. So what about quantum in biology? What about quantum biology? Now, we know that electron carries a spin and a nuclei carries a spin. So normally electron spins are not active because, for example, if you take a molecule, 2 electrons are bound into a singlet. So it's spin 0 state. Similarly, most of the time these electron spins are not there. But however, there are so-called radicals where there may be an unpaired electrons. Okay. You know that this year's Nobel Prize went to one of the Nobel Prize winners in physics, Roger Penrose, a great mathematician, a great physicist, very imaginative person. He wrote some years ago that he had a hypothesis for so-called measurement hypothesis in quantum mechanics involving relativity. We will not go into the details, but he came up with a great imagination, great thought that certain biological components, so-called microtubules, is basically a tube made up of proteins which are inside the cell. You can say they are like the bones of the stem. They carry a lot of dipole moments, so they are like some electromagnetic cavities. So he said the quantum character of those things will be very important, and perhaps that is at the heart of thinking and consciousness and so on. And many people laughed at it, even though many people laugh at it, because to speculate like that, it's because when you go to things like realms like mind and so on, you can become too easily too speculative. But one should be very careful, because if there is anything experimentally verifiable, then the whole world will accept. So there were a lot of, but the point is, I'm not saying that whatever Penrose said was right, but I'm saying he was bold enough to make the statement. But now you find, in addition to microscope, there are many, many places where quantum physics seems to be working. Like in photosynthesis, I already pointed out, the photons seem to be entangled. So people wonder whether nature is using quantum mechanics at room temperature in a very efficient way. It is definitely using in many enzymatic actions, like proton tunneling and so on, electron transfer. But is there more? Is there some cooperativity? Is there quantum entanglement? So it's a very heated field. A lot of controversies are there. But fortunately, in physics, when people start doing experiments, then comparing notes, it becomes respectable, and that's happening. I will tell you one beautiful thing about, we all see birds, man. Bangladesh is a beautiful country with green birds and water and so on. Birds fly long distances and they know which direction to go. They use sunlight and polarization, and also they detect the local magnetic field, feeble magnetic field of the order of 1 Gauss. So my friend Klaus Schluter, many years ago, he's no more unfortunately, he was in Urbana-Champaign, came up with a hypothesis that perhaps birds are using magnetic field at the warm wet room temperature the following way. So if you take in biology, there are lots of chemical reactions going on. So there are chemical reaction pathways. So he suggested there could be pathways in which the intermediate state could be a spin triplet or a spin singlet. As you know, 2 spins, like 2 electron spin, can form a singlet or a triplet. Now, if the spin is a triplet, the reaction pathway will go left. If the spin is triplet, the pathway will go in another way, right, let's say, figuratively. Now, the energy difference between the intermediate states is very tiny. It can be distinguished by Earth's magnetic field. The singlet triplet splitting, or so-called Zeeman splitting, is of the order of 1 Kelvin, 1 Gauss, magnetic field unit. But we are at 300 Kelvin. So he said, okay, that is true. But however, there are nuclear spins in the nuclei. And nuclear spins are well isolated from the environment. So they are not in the warm wet environment. They are somehow decoupled. They are at extremely low temperature, in a way of saying. So he said this nuclear spin will communicate with electron spin and use quantum physics. and will tell the bird eventually that this is a direction. It's like finding a hay in a finding a needle in a haystack. So quantum physics and what is interesting is about 5 years ago we were sitting in a quantum biology conference and George was there, and there was a presentation about experimental confirmation of this kind of phenomena. So I just wanted to tell you, there is for young people like you, there is a lot of opportunities in quantum. Quantum biology is just the beginning, but you should be careful not to fall prey to people who say that they can explain consciousness by quantum mechanics and so on. They are far removed. There are practical phenomena in photosynthesis, in proton tunneling, and various things in which people are worried about explaining this using quantum mechanics. You cannot escape quantum mechanics. Because originally people thought in biology, quantum mechanics stops up to bonds and reaction rates and so on. Now perhaps it's more than this. So that's one front. So there are many frontiers in science where quantum mechanics is coming in a big way, like quantum nanomechanics. See, engineers used to worry about big bars, iron bars, and so on. Now people worry about bars made up of like carbon nanotube. Carbon nanotube, its thickness can be 1 nanometer, maybe 10 nanometers. So it's like a vibrator, and it's a quantum vibrator. It has quantum physics, so it can use quantum mechanics. So mechanical engineers are studying it, chemical engineers are studying it. So let me finish my talk by saying that quantum mechanics is a great subject. At the beginning, for many people, it's repelling because it's counterintuitive. It looks like a set of rules. As great Feynman said, none of us understand quantum mechanics, but we know the rules of the game. But if you master the rules of the game, you can do wonders. But in the process, you get an intuitive understanding. You may not be able to explain it to others, but this is how science happens. Even I tell my people, when you read popular article about, let's say, string theory or about high temperature superconductivity, you may not understand it. The professionals understand. You develop your own intuitive understanding. That can take you a long way. So in that route, you can go a long way in quantum physics. And then finally, but I should also end by saying that it's very important not to ignore mathematics. Because mathematics finally is one of the important arms of physics and science. So it gives you power. So with that few words, let me conclude my talk, and thank you for listening to my talk.
Thank you, sir, for your wonderful and nice presentation. So if you allow, we can start our discussion session. So we have got some questions.
Yes, I'm very happy to answer questions. Yeah.
So the first question, so about maglev.
Please repeat the question.
What pushes the train forward? Okay, so about maglev, what pushes the train forward? We know that friction is needed for the movement of normal train.
Sorry, there is
as
a
you
problem
said in maglev. Okay, I can add the question in the screen. Just stop share. Stop share. I can add the question in the screen.
Okay, stop sharing.
Okay. So I think you can see it.
So where do I go now? Let's see.
In the streamer.
Yeah. You please type. Yeah, no, you can tell me. I hear you properly. Yeah. Please
so
tell me.
Can you see the question in the screen?
What pushes the train forward? We know that friction is needed. Yeah, exactly. So for every action, there should be a reaction, right? That's what we say. So it's like, let me repeat the question to the student. In the case of plane that's flying, there is a reaction. For example, if you take a jet plane, there is an ejection, right? So and also there is a turbine which is rotating. So in the same way, all those things will be there in this train. So at the initial stage, you may use friction to stick. After that, you can use the same principle used in aircraft and keep moving forward and accelerate, decelerate, and so on.
Thank you, sir. We have another question, so you can add this. So it's nice to hear excellent lecture from you, the creator of our theory of the high temperature superconductor. May I request him to say a few words about the present status of experimental and theoretical
Thank you,
field of
Sunil.
high temperature?
So, so it's a RBB theory. But now, let me just change the gear. Now the excitement is more with respect to new superconductor called the carbonaceous superconductor, because they have created a superconductor made up of hydrogen molecule, H2S, and methane under great pressure, like 200 gigapascal. Ranga Dayas, originally from Sri Lanka, is one of these leaders in this game. Great pressure, it becomes a superconductor at 15 degrees Celsius. I'm sure in some part of Bangladesh, in the winter, you will reach 15 degrees Celsius. I was very unhappy because in my city, we never go below 19. I don't know about Bangladesh. So it's room temperature for practical purposes. So they have reached superconductivity. It's an exciting time. Just it was last week. So about RBB theory, people say, as the early proponents of RBB theory, along with great Phil Anderson, it's in good shape, except that people are silent about it because there are many problems with the quantitative calculations, but the model that we have proposed is right. But many-body theory is still lacking. Physics-guided many-body theory already there. So these things are there, but it's in good shape. But the sociology of science is very strange. Now people's attention change and they get diverted in variety of new developments. Then come back. That's my short answer.
Thank you, sir, for your nice presentation and discussion session too. So I would like to say thanks again on the behalf of the Department of Physics, Pabna University of Science and Technology, sir. So the main aim of our international physics webinar is to motivate and encourage our students in this corona pandemic situation, and we are very, very grateful to you that you have accepted our invitation in this corona pandemic situation. So we'll definitely invite you on a face-to-face program in Pabna after the COVID. So thanks again. Bye for today. So
Thank you very much. So thanks to all the friends and thanks to you for organizing this. See, and also I would have expected students to ask questions, but like I think Indian students, Bangladesh students are also shy. So normally when I come out with the lecture, they crowd me and ask questions. Now today I have to come to your home.
yeah, thank you,
Can't
sir.
teleport
Bye,
myself.
bye
Anyway,
sir. Thanks
you are
again, sir.
welcome to send me email if you have any
Yeah,
questions. Yeah.
yeah. I'll send you, sir. Bye.